To hear from now. Jane had a long career as a scientist, geologist, and environmentalist at Lawrence Livermore National Laboratory, a number of other great places. Since she retired, she has pretty much devoted herself as an environmentalist to the crisis of climate, and she is now deeply involved with both national and efforts in California around rethinking our energy systems and how we need to respond to this urgent crisis. And she's done some very original research and thinking, so I'd love to hear her tell us about it now. So Jane.
Thanks. I'm not going to talk to you today about energy, but I am going to talk to you about the concept of intentional modification of the climate. And this is only one of the most complicated and difficult problems that humanity has ever faced, and so we're going to do it in 10 minutes. What I'd like to say is I'd like to tell you about why we're going to be looking at it, what it actually is, what the technologies are, how they might be used, and what some of the issues are in trying to get research started. So how many of you have ever heard of persistence of CO2 or the bathtub effect of climate? Have any of you heard of this? This is probably the single most important fact about climate science that people generally don't understand. When you put carbon dioxide into the atmosphere, it stays there, and it stays there for thousands of years. So this means that every time you drive your car, you are putting something like 33 tons of carbon dioxide. Every time you use up a gas tank, 33 tons or so of carbon dioxide in the atmosphere, and it's going to stay there for your children and your grandchildren and their children. So what that means is we have a carbon budget. There's only so much carbon that we can put in the atmosphere before we reach these putative limits on temperature increase. And right now, we are only years, maybe a decade, maybe two, away from surpassing 1.5 degrees or 2 degrees Celsius. So that means we're headed for a climate crisis no matter what we do. We have bought a climate crisis. We do need to stop emitting as fast as we can to avoid this. But right now, this is what emissions look like worldwide. What you see here is some slight decline in the United States, mostly due to fracking. Fracking has brought gas into the electricity generation market, replacing coal, which has caused a significant decline in US emissions. But worldwide, they're going up, which you see on the left-hand graph. And if you can look on the right, it's largely due to what's happening in China. So no matter what we do, we have a worldwide problem in emission increase. We're not going to do that. So what do we have to do to stay below? This is IPCC, or these are UN results done by many, many scientists who look at trying to understand how we could reach these limits. And what you see in the red curve is what would happen if we continue as business as usual, and we have to get to the blue curve of emissions per year to stay below 2 degrees. And what you see is that the conventional mitigation methods that are under consideration will take us part of the way there in the gray zone, but the blue zone are emissions that are going to be very hard to get rid of. And all of the model results throughout the world showing how we can stay below these limits now show intentional modification of the climate in some way. They use the models generally use a withdrawal of carbon dioxide from the atmosphere, but there are other technologies that could also bring us there. We will have to consider, my view is we will have to consider climate engineering to stay below these limits. There are two kinds of technologies that are under consideration now. One is called negative emission technologies, and these technologies actually withdraw carbon dioxide from the atmosphere. There's like going back in time. So we bring our climate back to a previous state. The difficulty with all of these technologies, direct air capture, taking CO2 out of the air and then putting it underground, growing crops, using those crops to produce energy, capturing the CO2 from the flue and putting that underground, and growing crops and artificial fertilization in the ocean, all of these are very, very slow and very expensive. For example, if you burn 100 gallons of gasoline in your cars, you're going to produce about a ton of CO2 in the atmosphere. To get that ton of CO2 out of the atmosphere, and that will produce about 13 gigajoules of energy. Sorry, not gigajoules. Sorry, I have to, when I'm up here, it's hard for me to do. Petajoules. No, that's not right. Gigajoules, yeah. It is gigajoules of energy to burn that 100 gallons of gasoline. If you now want to capture that and take it out of the atmosphere, you're going to have to use 5 to 10 gigajoules of energy. So it's a very difficult thing to make that equation work financially, not to mention from the engineering perspective. We do need to do this. We will need to do that. We need to do more research on it. The other way is to cool the planet by reflecting some of the sunlight that comes into the Earth. And that stratospheric aerosol concept is to put usually sulfur particles into the stratosphere and allow those particles to reflect sunlight back into the atmosphere, thus cooling the Earth. And we know this works because volcanic eruptions often produce sulfur particles that go into the stratosphere. This is the Pinatubo eruption in 1991, which cooled the planet by about 1 degree for a number of years. So we know that we can do this, and we also have done some feasibility studies to show that we could actually get that amount of particles into the air. So we also know that these methods, by calculation, we can see that, for example, on the upper left, you see what would happen to the Earth, how it would get warmer if we quadrupled the amount of carbon dioxide in the atmosphere. And on the right, you see what you could do to return the Earth to a temperature realm that was more like what it is today by using aerosols in the stratosphere. And we also know that precipitation could be returned to something closer to today. But these are very problematic technologies for a number of reasons, because we don't know exactly how they're going to behave. Another idea is to brighten clouds, and we know that clouds get brightened also with aerosols because we can see the tracks of ships that go across the ocean because the exhaust produces aerosols and causes those clouds to brighten. So we know we have some technologies that might work. So what is the role for this? Business as usual, the climate impacts are going up and up. We need to cut emissions. That's the first and most important strategy for dealing with climate change. But we probably are going to have to remove some of this carbon dioxide from the atmosphere. There's a bunch of technologies that might do this. As I said, they're very slow and expensive. So we're looking at a period of time when temperatures might exceed what we're really able to withstand. And here's where solar geoengineering might come in, to cut off the peak. If we don't do mitigation and we don't remove the CO2 from the atmosphere, we can't use these technologies because the impacts of the carbon dioxide in the atmosphere will increase and increase and increase. And so you'll have to put more and more aerosols into the stratosphere, in which case you will have you will go farther and farther from known climate states and higher risk. But if we are using these together in a concerted strategy, it might be possible to manage this crisis. So what are the things we have to think about? We need to do the research. We need to inform future decisions. People say if we do this research, it'll make these technology applications inevitable. But my concern is that we are going to do them anyway, and we need to know more rather than less. We need to learn how to be strategic about climate. We're not going to solve this problem by incremental and emergent technologies. We have to be strategic on a large scale. And one of the things about geoengineering is that it's inherently strategic. So when we engage in this kind of research, we can begin to learn to be strategic. People are already considering doing these kinds of interventions. They're considering doing them on a regional scale. The Australians are considering saving the barrier reef with cloud brightening. Indonesians have used technologies to rain out storms so they don't flood. People are thinking about technologies to save the Arctic, to keep the Arctic from melting. These are already under consideration. They need to be informed by better research. We need to start low-risk research now. We don't need to perturb the climate of the Earth to understand a lot more. We can do a lot of modeling work, and there's an awful lot of physical and chemical processes in the atmosphere that we don't understand very well that we have to do research on. and those are low risk. But when we start these, this is the perfect opportunity to also start to learn to govern this technology. We need to start research governance and grow research governance into governance of the technology now. And this means changing the way we do the way we do research. This is not curiosity-driven research anymore. This needs to be mission-driven research, systematic research, and it needs to be, in the words of our LinkedIn friend yesterday, we need to have clarity. This community uses the word transparency, and I have always been a little bit skeptical of transparency because to most scientists that means putting all their data on the web, which is a meaningless thing for society. So we need to learn how to clarify what this research means to the public as a research community. So if you have questions, I'm happy to take them offline, and I hope you get interested in this topic. Thank you. You're welcome.
Really good. Thanks so much.
Good.
All right. Well, I would just go straight into our next session. Thank you, Jane, because that geoengineering topic, one of the things she didn't mention is how inexpensive it is to do, which is one of the things that makes it all the more urgent that research be done because, as she mentioned, Indonesia, they already tried it. Rich people could do it independently as individuals.